Welcome to the course of assembly programming languages and their principles, or in a bigger term, machine languages. And today we're going to talk about the way data is represented in hardware, and specifically about hexadecimal arithmetic. And I already started the course with giving this joke. Some people may understand it, for some people it doesn't make sense, but anyway, there are 10 kinds of people: those who understand binary and those who don't. So what exactly is meant by that? So if we look at the number 2, well, it's just 2, right? It's 1 plus 1, right? Now if we look at the number 10, then there actually could be different understandings is what's meant by 10. It could be equal to 10 in decimal system. I'm going to use the index under here to show what system is that. Or it could also be equal to 2 in decimal system if I assume 10 to the 10 or 10 to the 10 in binary system. So what is a binary system? The binary system is something that contains only ones and zeros and ones. Okay, these are the only 2 digits for the binary system. While for the decimal system, we always know that we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, 10 is not a digit anymore. 10 is a number, right?
0.
So 0 I already wrote. So altogether we have 10 digits here, right? While here for the binary we have only 2 digits. So it turns out we can have other systems as well. We can have an octal system where we only have digits from 0 to 7, right? 0, 1, 2, and so on. Altogether 8 digits. That's why it's called octal system. And many other systems. We can have also hexadecimal that we're going to talk about today. That's system that has 16 digits. Imagine that. 0, 1, 2, 3, 7, 8, 9, and then A for the 10, B for 11, C, D, E, and F for 15, right? So this is sort of the 15th digit. Altogether, there are 16 digits for the hexadecimal system, right? Now, why would we do that? If we think about modern computers, it's much easier for them to calculate things, to try to process data if we represent the data as on or off. Right, so it's like true or false, or there is voltage, some sort of voltage, or there is 0 volts. Right. In other words, 1 or 0. Right. And rather than having, say, different voltages for the decimal system represented directly on the hardware. Right. Right. So that's why we are using binary system in computers. Now, how do we get the actual values? If I were to write down 0, 1, 2, 3, 4, 5, 6, 7, and so on in the decimal system, right? So then in binary system, it would be 0. Well, 0 is 0. 1, there's no difference here. Now, for the 2, we have exhausted all the combinations with just 1 digit. So we have to move to the next digit. So therefore, 1, 0. Okay, so now for the 3 we can do 1, 1, and again for 2 digits there's no more possible combinations. I mean, you could imagine that here we sort of have in front of these guys zeros. Okay, so that's why we need to move to 3 digits, right? So this is going to be 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And for 7, again, this is the last one. And for 8, we would again have 1, 0, 0, 0, and so on, right? That's how we count in binary. And that's where the joke is coming from. 2 is the same as 10, right? Now, if you know how to count in binaries, then that makes sense. And if you are a programmer and dealing a lot with low-level programming languages or low-level software development or drivers or hardware, then you're very well versed in binary system, right? And that's when this joke actually makes sense. All right, so if we look at the counting systems in general, turns out we can represent any system by using its base b here, and we can calculate its value using these formulas. Okay. All right. So talking about counting systems, we can represent or we can calculate any a value for any number in any counting system. So we were talking about decimal. We're talking about binary system. We're talking about octal a little bit, even though I didn't show you how to count in octal. And we will be talking about hexadecimal as well today. Right? All right, so in all these systems, for the decimal, the base is 10. For binary, the base is 2. For octal, the base is 8. And for hexadecimal, the base is 16. Now, when we know the base, we can actually calculate what the value of a number is. What I mean by that is, if I write something like 1, 2, 3, then 1, 2, 3 actually is the same as, according to this formula, 3 plus, so this is coming from this term, right? And then this is going to be 10, this is going to be 10 to the square, and so on, right? So 3 plus 2 times 10 plus 1 times 10 to the square, which is indeed, this is 123. So there is no big surprise there because we are very used to the decimal system, right? Now, what if I write something else? What if I write something in binary? Let me write something like 1011. Okay, so 1011 in binary system, its value in decimal system would be what? It would be, again, I'm gonna start from the least significant bit and I'm gonna go to the most significant bit, right? So there the order is kind of the opposite in the formula. And let's see, so it's 1, it's this one, okay, times 2 to the power of 0, right? So this is like 3 times 1 here. Plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 3. Okay? So let's see, let me do a little calculation here. So this is going to be 1, obviously. This is going to be 2, this is going to be 0, and this is going to be 2 to the 3 is 8, right? 8. So therefore, the result here is what? The result is 1 plus 2 plus 8. So it's 11. Right. So again, only 1 and 1, only 2 digits. I should have chosen, I guess, a better example, but what can you do? Turns out we can also write the same value using a slightly different formula, right? Again, if we were to write 1, 2, 3 in decimal system, then we could calculate its value using this second formula. And that would be, see here, A0 is 3, so therefore it's equal with, 3 plus base is 10 times A1 is 2 plus base is 10, and A3 in our case, I mean A2 in our case, is 1 plus, and I believe that's it. 1, yes. 1 plus 0, you could say. So let's use all the parentheses to close it up, and now we can calculate. So 1 times 10 is 10, plus 2 is 12, times 10 is 120, plus 3 is 123, right? So it's the same result. It's just the grouping of the additives is rearranged using the parentheses here. Same formula. Now we can use the same formula again for other counting systems. So we could have fun and have a little bit in octal system. So in octal system we have only 8 digits, not the 10 digits, right? So they go from 0 till 7, right? So what if I write 1, 2, 3 in octal system? What would be the value then? Okay. And again, we can do the same formula as we did before. Let me choose a different color, just for it to stand out a little bit. So that would be, in this case, 3 plus 8, not 10, times 2 plus 8 times 1, parenthesis closed. So therefore, again, we can calculate 3, so 1 times 8 is 8, plus 2 is 10, right? So this is 10, 10 times 8 is 80, and plus 3 is 83, see? So in octal system, the value will be 83. In decimal system, the value will be 123, much bigger. So we need to know which system are we writing the numbers in order to see what the real value is. Of course, for the computers, we're mostly going to use the binary system, and then we sometimes are going to use the hexadecimal as well. Right. Are there any questions at this point? If there are no more questions, let's move on. All right. So where is the base? Are you familiar with this old expression? All your base are belong to us. Do you know this one?
No. All your base are belong to us?
Yes. So if you want to learn more about this, you could search eventually on the internet for that. But this is from a really old computer game. You know, when computer games just started to raise, there was this game which was translated to English sort of clumsily, and that's why, you know, even this expression is not perfect by far, right? All your base are belong to us. And this was the message when you, I guess, lost to the aliens in that game or something like that, right? But the expression was so, you know, so twisted, so that it got very popular in the culture of computer gaming, you know, old computer games. Anyway, that kind of pop culture. But in our case, the base, where is the base? We already know that base is what we mean 10 for decimal and 2 for binary and 16 for hexadecimal and so on, right? When we're going to write our numbers, we're going to use the base as an index down here, right? So that's where it is. That's how we know how to look at that number. And I have done that already in the previous slide. Now, when we go to different computer programming languages, such as C or C++, we can show the base that we are using in some other ways. So for example, if I have 0 in front of a value, that means it's an octal constant, right? So therefore, let's say if I have 1, 2, 3, then the value in C is going to be 123. However, if I write 0, 1, 2, 3, then C is going to consider this as an octal constant, right? So this is octal. And therefore, the value is going to be what? Let's check it out. It's 83. Okay? So it's 83. Now, if we are to write a hexadecimal, then we're going to start with 0 and x. And it doesn't matter, the lowercase or capital, I suppose, right? So if I'm writing 0x, 1, 2, 3, then we need to calculate actually to see what the value is, all right? And I suppose we could do that. So this is equal to 1 times 16 to the 3 plus 2 times 16 to the 2 plus 1 times 16.
I think it's 16 to the 0, 16 to 1, and 16 to 2.
You're right. You're right. So 16 to 0, 16 to 1, and 16 to 2. And thank you for that. That's because right. It's going to be much easier to calculate as well, right?
It's like 256.
250. All right.
Yeah, 16.
So this is going to be 2 times 16.
Oh, yeah. 32.
Right? So that's 32. And this is going to be 3 times 16, which is what?
3.
3 times 16 to the 0 is indeed 3. Right. So let's add these guys together. What do we get? We get 288 plus 3. So 291. See? The value, so that's in decimal, right? For 123 in hexadecimal is much larger than in decimal. Right. Now these are the 3 ways, the 3 most popular ways how to write constants in C and C++, and in fact many other programming languages accept this format, right? Now in assembly languages, we also may want to write binary numbers, and in fact in C also you could write binary numbers, except now you have to prefix them with 0b, right? So what if I write 0b 1, 2, 3? Would that be okay? Could we figure out what the value is?
No.
No, we could not. And why is that?
We have only 0 and 1.
Indeed, we only have 2 digits that we could use in this binary system, right? So therefore, this is a silly example, right? So let's write something else. If I were to write 0b 1, 1, 0, 0, okay, let me choose the blue again. Then it would make sense for me to talk about, you know, okay, what's the real value? Now, since this is a binary number, so then I can do again this. 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0, right? Which is equal to 8 plus 4, which is equal to 12 in decimal system, right? So, okay, in decimal system. All right, so now it is time for an exercise, right? So let's consider this example. There are 1, 2, 3, 4, 5 different values, numbers rather, right? What I would like you to do is to calculate what are the actual values for these numbers, right? And post them in chat private to me.
Which system do we convert it to? Decimal?
Yes, to decimal. So right now the values, you know, as humans, we are the most comfortable with using decimal system. All right. So I'd like you to do 74. Well, I can do that one for you. So 74 is a decimal number, so therefore the value for it is going to be 74. Now 0, 1, 1, 2, what system is that?
It's octal.
It's octal, indeed. And it's octal because it starts with 0. So go ahead and calculate for that, and also go ahead for 0x4a. And for this, I would like you to use your, you know, pen and pencil rather than a calculator, because it's very easy to do that and calculate on using the calculator. But when I give you a test where you have to actually do these things, you're gonna actually have to show how you arrive to an answer. All right, the answers are coming in, and let me just finish this guy here. So this is 0b 1 0 0 1 0 1 0, right? And then there is apostrophe J for some reason. So this is binary, and this is something else that we're going to talk about in a while. All right, and seems like you are getting there. Are you getting the right answers? Meaning that what is 0, 1, 1, 2? So this is the same as 8 plus, so this is an octal constant, so therefore it's going to be 8 to the square plus 8 to the first plus 2, right? Because there is 1 and 1, so we don't change anything here. And if we add these guys up, so this is 64 plus 8, so this is going to be plus 8 plus 2, so this is indeed 74. All right. Now for this 4a is going to be 4 times 16 plus a, and a has the value of, so remember, for the hexadecimal, we had 0, 1, 7, 8, 9, A for 10, B for 11, and so on till F for 15. Okay? So therefore A is the same as 10. So again, 4 times 16 is 64. 64 plus 10 is again 74. It's like magic, same value, right? Now for the binary, let's check it out. Sometimes in order to do binary, it's easier for me to write it like so. So what's the value? I'm gonna write it under here, okay? So 0 doesn't matter. So this would be 2 to the power of 0, so that would be 1, 2, 4, 8, 16, 32, 64. Okay, so from here I see that 1 is here, 1 is here, and 1 is here. Okay, so again 64 plus 8 plus 2 is the same as 74, right? And J, now J is actually a symbol, and as we're going to learn later in the class, every symbol has a code. There's a way how to encode these symbols, and one way how to encode the symbols is using ASCII encoding table. This is one of the most popular, I guess, right? Meaning that every digit, every symbol has a code, and if we actually go to ASCII table here, so I'm gonna go to a different one, ASCII table at the Carnegie Mellon University, CMU, right? We can see that every symbol has a code. Here the code is in decimal, for example. If we look for J in this table, the capital J, it's 74 again, all right? And if we were to look for the capital A, it's 65, for example, right? And so on. So the answer here is, once again, 74. All right? Okay. Are there any questions or comments, perhaps? There are no comments? Well, then let's move on. So there are examples for various bases and, and how to calculate the values. Where if we would consider 110 as the binary, then again we can add them up as 1 times 2 to the square plus 1 times 2 and so on. Then the value is 6. We could play with different kinds of bases. For example, at the base of 5, all we do is we substitute base with the 5 and we get a different value. Now this base is not going to be very useful in computer science because mostly, as I said before, we're going to use the binary, the octal, the hexadecimal, right? And for those bases we have again different values here that we can calculate using these formulas, right? Why is this so important to talk about binary system? Right? So in electronics, it's much easier to represent whether something is on or off. We could represent, if we were to talk about decimal system, let's say if this is voltage and if this is time, we could divide the voltage in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and represent the numbers with various degrees of voltage. For example, I could do 0, then I could do something like 5 here, 9, maybe 8, maybe 7, maybe 2, and so on, right? As the time moves on, I can change the value on the wire and do some sort of calculation. Could this be done? It could be done, and people have tried it. Would it be faster to calculate? Seems like, we only need 1 digit. In binary system, we would have to have 4 digits. Since this is happening in analog domain, it would take time for the, let's say, addition, the analog addition to happen, right? So it could be made pretty fast, but I suspect that it will still be faster if we are using the binary. But it would be really, really complex to implement this, and it would not be energy efficient. If you know about electronics and CMOS devices, we could discuss that. But that's a different course, different topic. Right? It's much simpler for the computers, really, for the digital devices to think in terms of 0 and 1, right? And we're going to call them bits, right? 1 bit is either yes or no, either 1 or 0, either true or false, either on or off, and so on. Okay? And sometimes we can talk whether it's magnetized or not. If we talk about magnetic storage, such as hard drives that are using the magnetic media, those that have these spinning platters on them. Bright or dark, if we're transmitting information over fiber cable, which is being done under the ocean, for example, there are a bunch of fiber cables running, sending data, information between the continents, and so on. So ones and zeros is what we do at the computing level. Right? There could be different stories. Sometimes you encode information using more states and so on, but that's a different story. Okay. Now, how do we call these, bunch of of bits. We can have 8 bits, which is going to be a byte, right? So for example, if I write 1100 1011, so that's 1 byte of information, 8 bits altogether. We can have a word that's 32 bits, right? Why is that? Because quite often there are microprocessors in computers that have 4 bytes of information that represent something, useful. For example, this could be an instruction. It's like a command for the processor that tells what to do. Or this could be a register that holds a value, right? So historically, 4 bytes are called one word, right? So for the convenience, there's also this half word if we are just using just 2 bytes, right? And then there is double word for 64 bits, meaning 8 bytes, if we need to, some bigger numbers or higher precision information. So these are the names that we are going to use during this course, and also that are being used in many programming languages. You can define a data type that is a double word, for example. Actually, if we are talking C and C++, if we're talking about double data type, that's actually a double precision floating point number. It's not necessarily the double word, so be careful. And there might be other names, right? Are there any questions or comments, perhaps? Okay, so this is how we call these guys. Now, what's wrong with the binary system? We just decided that binary system is gonna be pretty good.
It's Lucas.
So for the computers, for the hardware, binary system is just perfect. On or off, they can deal with that. We can build simple systems. Based on those, we can build complicated systems, and in the end, we can build computers and computer networks and all kinds of good things. Now, for humans, there's a lot of digits, so it's too tiny. It's not so convenient. If we look at this number, 110, 110, 100, it doesn't really jump at us like what the value of it is, right? It's not so obvious, right? It would be nicer if we could just write maybe in decimal, because we're so used to it, or maybe something close to decimal that's still easy to use, because for the decimal we have to do quite a bit of math to go back and forth between binary and decimal, right? Maybe there's an easier way. And therefore, there are 2 typical choices. One is the octal, and one is the hexadecimal system for encoding numbers. And why are these choices so convenient? Because for the octal, we know that every 3 bits is going to represent 1 digit, right? For hexadecimal, every 4 bits is going to represent 1 digit. And why is that? Because in octal system, we have 8 digits, right? Octal, obviously, which is the same as 2 to the power of 3. For the hexadecimal, we have 16 digits. And again, it's 2 to the power of 4. Same thing. Same principle anyway, right? Why is that? Because it's, if we're using binary system, and if we're using just 3 bits, then the number of different combinations that we can show or write using just 3 bits is 2 to the power of 3. Right? So that's why we can group the number in 3 bits, And then we can easily figure out what the value of it is in that particular counting system, right? And we can go back and forth. We can easily go from binary to the octal, and we can go from the octal to the binary, right? So let's try it again. Let me do 1, 2, 3 in octal. What would that be in binary? So for the 1, it's 0, 0, 1. For 2, it's 0, 1, 2, 0. And for 3, it's 0, 0, 1. Sorry, my mistake. 0, 1, 1. So 123 in octal is this number in binary system. It was very fast for me to convert. I didn't have to do much math at all. All I need to know is what are the representations of each of those digits in binary system, and that's actually fairly easy to figure out, right? So 1, 2, 0, 1, 2, 3, 4, 5, 6, 7 in octal is the same as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay? As simple as that. Now, if I were to go the opposite direction, let's say I have some sort of number 1, 1, 0, 1, 0, 0, 0, 1, 0, something like that. Okay? Again, I could group it in bits of 3, and I can write the value. So this would be 4 and 2 is 6. This is just 4. And this is 2. All right. So by the way, if you know about Linux operating system, there are files in Linux operating system, and every file can have different permissions, whether people can write or read and execute the file. All right. And there are 3 groups. So there's the owner of the file, 3 kinds of users. There's the group of users, and then there's everyone in the world, right? User, group, and others. Right? And every group, every of those categories has 3 bits assigned to what they can and what they cannot do. And the meaning of these categories are whether they can read, write, execute. Read, write, execute. Read, write, execute, right? So now from these permissions, you can very fast and very easy to actually calculate based on what people can or cannot do. So for example, if we want to allow the user to do everything, so read, write, execute, and if we want to disallow for the group and for the rest of the world to do anything with that particular file or directory, then this is the user group. So therefore the actual value for that one number that represents these permissions would be 111 000 000, and in octal system it would be 700. And now in Unix, in order to set the permissions, there is this command. It's called change mode. Change mode, right? And in that command, you could write 700 and my file, for example. Right? So that command is actually using the octal system, just because it's so easy to and quick to convert from the meaning of permissions to the actual value. Right? There are other ways to use this command, but this is one of the representations. All right, so for the hexadecimal system, we do the same, except we group 4 digits. So we're going to have 4 digits here, 4 digits here, and 4 digits here, but except there are no 4 digits, so I assume the rest of them are zeros. So this is 0, 1, 0, 0, so it's 4. This is 1, 0, 1, 1, so this is there I have to think about it a little bit. But I could also calculate
11.
it. So this is, so you said 11. How did you get 11?
It's like 8 plus 2 plus 1.
8 plus 2 plus 1. So indeed it is 11, right? So it is 11. And now for the 11, what is the letter for hexadecimal? Can you tell that too? It's B, indeed. And here we have this 1, so therefore it's 1. So it turns out this number is the same as 1B4. It's the one before in hexadecimal, right? So the point here, once again, is we're using these representations of the number because it's very easy, very fast to convert between them, and because it's much more, representative for us humans to see how big is the number is if we see, let's say, 123 versus if we say just a lot of bits, ones and zeros. All right. So should we use octal or hexadecimal might be the question. And octal seems to be, both are easy to convert, as we just found out. Octal is a bit closer to decimal. There's only, from 8 to 10, there's pretty close. But the problem with octal is that it converts 3 bits, while in computer systems we're usually dealing with bytes, which is 1111, 1111. This is a byte. And if we were to use 3 bits, then it's going to be either too short with, 6 plus 6 is, 3 plus 3 is 6, or too long, 3 plus 3 plus 3 is 9, while a byte has 8 bits. So that's why people have found out that it's kind of more convenient to use hexadecimal system, because then every 4 bits can be represented with one hexadecimal digit, FF in this case. And by the way, we know about bits and bytes. If 8 bits is a byte, then what is 4 bits? So 4 bits is a small byte, you could say, right? A small byte. It's a nibble. All right? So this is called a nibble. 4 bits. And you can find that word as well. Not as often as bytes and bits and so on. Right? Okay, so we're going to be using hexadecimal for this reason. Okay. Now, if we're looking at 111, 111 in octal system, so in octal system it would be 7, 7, and 3, 3, 7, 7. That's how we got this number, right? But in hexadecimal it would be F and F, right? We don't need to imagine any extra bits here. Okay, so if we look at the hexadecimal system, here you have a table of all the digits starting from 0 till A, which is 10, and all the way down to 15, which is represented with F, right? In binary system, this is 1111. That's easy to remember. A is not so easy to remember, but we can always calculate using the powers of 2. This is 1, 2, 4, and 8. 8 plus 2 is 10. So therefore it's A. And so on. So these are the values we're going to be using in this course, and also in programming when working with computers and low-level programming languages. Now, we know how to convert from any base to base 10. In the beginning of this class, we did that already, right? And if we look at the hexadecimal system, there's nothing different really with that. So again, we have base to the various powers, 1f4. So we write 4 goes here, f is 15 goes here, and this one goes over here. I'm exaggerating a little bit here. Okay. And then we add things up and we get the actual value, right? If we have a bigger number, C and D, C would be 12 and D would be 13. So again, we can calculate this value, right? Now, if we know certain values, we sometimes can do the calculation a little bit faster, right? So for example, let's say we know that 116 is the same as 256, right? And sometimes, you know, people start remembering things like f0 is the same as 240, right? So then if we want to calculate one f4, then we could think of it that this is pretty close to 200, very close. In fact, it's only by 13 less than 216, 200 in hexadecimal. So therefore, we can write the same thing as 200 minus C, right? So C is equal to 13, by the way. Meaning that 4 plus C is equal to 10 in 60. All right? Now that we know that,
I think C is equal to 12.
I think you're right. Thank you for correcting me. Yeah, so this is indeed 12. Yes. A, B, C, 10, 11, 12. Yeah. Thanks. All right, so anyway, so 4 plus 12 is 16, so which is the same as 10 in 16 in hexadecimal, right? So now that we know that, we can actually easier calculate. We know that 200 is 512, because that's something, you know, you can get from the example above. It's 2 times 100. And then this is the 12. This is the same as C, right? As you pointed out. And again, 512 minus 12 is 500, right? So sometimes it is faster to convert things this way. Not all the time, but you know, if you can see that the number is pretty close to, you know, some round values, then that helps. Other questions or comments? All right, well then, it is time for the exercise. Please do convert these to the decimal system and send the answer private to me in chat. Okay? I'm going to give you a couple minutes for that. All right, so I see that the answers, many answers have come in. Let's see what I can do. Okay? So 125 in 16. How would we convert that? So one way would be to go, it's 16 to the power 2 plus 2 times 16 plus 5, which is 256, right? Plus 32 plus 5, which is 288 plus 5, which is 293. That's what I'm getting. Seems like you are having the same answer here. Okay. All right. So now this one, the 400 seems to be a round number already. So I can, you know, cheat a little bit, or better yet, be smart a little bit. And remember that 100 is 256. Okay. And therefore, this is going to be 4 times 256, which is 124. Now, this also happens to be 2 to the power of 10. Okay? And I know that, for every digit, we can take 1 power, we can take 4 powers of the 2 and add them up. And here I see that 4 is the same as 2 to the power of 2. So therefore, the whole value is going to be 2 to the power of 2 plus 4 plus 4. Because these are zeros, meaning that they are full numbers. Okay, so that's another trick that you may want to use sometimes. All right. In other words, I'm just counting how many bits are there with 1, and I know that 1, for example, in the next example, it's going to be convenient for us to write out 7, which is 111, plus f, which is 1111, plus f, which is 1111. Okay, so all together we have 4, 8, 11 bits. All of them are ones. I could write down that this is the same as 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Minus 1. If I subtract 1, then I end up with this. It's just like if you have 1000 and subtract 1, then the answer is 999, all 9s. So in binary system, that would be all 1s. Okay? Now for this, I can easily figure out the value because it's 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that right?
Yeah, it's 2 to the power of 12.
12. 2 to the power 12 minus 1. All right? And then you can do a little bit of calculation and you can figure out that this is 32,767, something like this. Right. I see that you have a similar answer. Same answer here. Now for this guy, this is a really long number once again, right? So, but the idea is going to be the same here. So this guy is again 2 to the power of, rather than 12, it's going to add another 1, 2, 3, 4, 5, 6, 7, 8, 16, 2 to the power of 32 minus 1. That's what the value is going to be. Okay, so this formula would have been sufficient for me to get.
That's actually weird. 2 to the 12 isn't this number.
Okay, so then it's probably 2 to the 11th. We have to be a little bit careful.
No. It's like too little. 2 to the 12 is only like around 4,000.
Okay, let's do a smaller example. Let's do just.
You missed the last number. You missed the 7. So it would be one more instance.
You're right. Right.
0, 0,
yes.
1, 1, 1.
Yes. Okay. So I missed.
Yeah, you missed one. Now it should add up.
Makes sense. Makes sense.
2 to the power of 16.
Okay. Okay, makes sense. So let me fix that. And so that's
16. Oh, sorry, 2 to the power of 15.
Right. So this is F, and this is the 7, right? From this guy. If we write it out in bits, that would be the value, but this is the same as this big guy minus 1. So therefore it's 2 to the power of 16, not 12, minus 1.
15.
15.
Yeah.
Because
we
yes,
have like 15 ones.
Okay.
And first one is to the power of
Right.
0, so
Right.
15.
And this is 32,767. correct? Okay.
Yeah, yeah.
And the same goes here. So this is 2 to the power of 31. Let me just clear it and write it down once again. So this is going to be 2 to the power of 31 because we have 31 single bits here. And minus 1. That's the same value here. And that's going to be a really large number that I'm not going to write down. But that's the point, how you get there. Okay, any questions? Okay. Now, what if we want to go the other direction from base 10 to base 16? Well, then the trick is to use a division and keep track of the remainder, right? For example, we could try this number. We divide it with 16 the first time. The result is this one, and then the remainder is this one. Okay. Then we take this result and we divide this guy with 16 again. We get the new remainder. Then we take this guy and we divide by 16 again. And then this guy and try to divide it by 16 again and get the remainder and the result. Until the result is 0. So when the result is 0, it means that there is no more sense for us to keep the division, right? And then once we have done that, then we just write down these digits, 3, 5, 7, and this is actually F, in that order to get the actual hexadecimal number, right? So it's 3, 5, 7, F in hex. Right? Just as the result is here. Okay. Now, how about another example? If we take this guy, looks like a pretty large number, we divide it with 6. That's the answer. The remainder is 9, and so on. So now the result is going to be 3 D 4 9 in hexadecimal, right? So it is a little bit of tedious if you need to do this division by hand, but in any way, this is how you do it. This is how you convert from the decimal system to the hexadecimal. So next time there is going to be a quiz where I'm going to ask you to do these conversions for different numbers. From the decimal to the hexadecimal, from the hex to the decimal, maybe octal system, back and forth. So you should practice, right? For example, there are a few numbers that we could use for practicing. Okay? So let's just try this this one number. Okay, so why don't you try and figure out what the result is? I'm gonna give you a minute or so. All right, so let me try this as well. So 199, let me try that one. Okay, so 1999 in decimal. Oh, I want to know what is this in hexadecimal. Okay, so one way to do that is to do the classical way. We just divide it by 16, just as we did it before, right? So we divide it by 16, and we see that we can have 16 ones in here. And the remainder is going to be 3. Okay, remainder. And then what we have left over is 339. Okay. So the result is 1. 39 here we get 2, so it's 32. So in fact, I was too quick with the reminder, sorry. And that's too early. I haven't finished the division yet. And here the 9 minus 2 is 7, 79. And here I can fit it 64 times, so therefore 4, right? And here we have 5 and 1. Okay? So apparently the remainder here is, at least what I'm getting, is 15, the first remainder. So that means the most significant digit is going to be F. That's the most significant digit. Don't make that mistake. It's not the least significant digit. Okay. Remember that when we did this conversion, the least significant digit, right? So the first remainder goes to the least significant digit. The last remainder is the most significant digit. Okay. I can see that some of you have made that mistake. All right, so this is F then. Now we have 124, and we need to divide that with 16 by 16. As it's going to turn out, 128 does not fit, so we need. It's not going to be 8, it's going to be 7, I believe. 7 times 16 is how much? Is 100 and is basically no, sorry, it's gonna be 100 and now this is the time when I would like to bring out my calculator and do the multiplication using that. 112. Okay, so this is 112 actually, right? Please do check whether I'm mistaken or not. Okay, so that's the result so far. And what's the remainder? So this is 2 and this is 1. So the remainder is 12. And 12 is ABC, right? And then the final remainder, 7 divided by 16. The remainder is going to be 7, and the result is going to be 0, obviously, right? So therefore, the answer is 7CF in 16. Okay? So apparently, Vitaly, you need to rethink your calculations. Looks like Robert and Lucas got it right. Okay. All right, so that's the result. And I advise that you do practice later with the rest of the numbers and perhaps even come up with your own numbers. Now, what if we want to add or subtract using a different system, such as the hexadecimal system? And in fact, it's just like the decimal system. The only difference is that the sum, when you need to do the carry, is 16. So the carry value is 16 rather than 10 for the decimal system. Meaning that if 3 plus 9 is 12, 3 plus 9 is 12 in decimal, right? For the decimal system, we would have the carry. We don't have the carry for the hexadecimal because this is less than 16. Okay, so rather, the result is adding these two numbers would come to what? A, B, C, right? So the result is C with no carry. Now, of course, in this example, we are doing the subtraction. So for the subtraction, Again, it's the same algorithm as with the decimal system. So we try to subtract 9 from 3. We cannot, so that's why we need to borrow 1 from here. And when we are borrowing, we're actually borrowing 16 in decimal or 10 in hexadecimal, right? So therefore, 13 minus 9 is the same as 16 minus 6 is the same as 10. So therefore, this digit is going to be A, right? And so on. So the subtraction is just the same as in decimal system, except remember that the digits add up to 16, not up to 10. That's the carry value. All right. Now, if you're a C programmer, there are some, smart things you can do, or quick hacks, if you will, when we need to convert between different bases. And one way is we can call sprintf string print formatted. So basically, we're going to print, rather than printing to a file, we can print to a string, to a buffer in memory, right? And then we can provide the format. %x would be for the hexadecimal. We can provide formats such as it should start with 0x symbolically, and then have all the zeros filled in up to 8 digits, and x would again mean use the hexadecimal and so on. So if you know what the format string is, how to use the format string, and you can read that in the manual for the printf functions, then you can use sprintf for the quick convert. Now there are dedicated functions for converting between different bases, such as a to I, L to I, and so on, meaning that string to integer. Okay? Or you can use string to unsigned long. str to ul, that's what it stands for. Okay? And the parameters for this guy is basically the string, the buffer, the number that we need to convert, the pointer to the actual buffer where we want to write, but to the end of the buffer apparently, right? Because we're gonna, when we calculate, we figure out things from the least significant digit, right? And also base, the kind of base that we want to convert from, right? And the bases could be actually quite wide range between 2 and 36, right? And there are some advantages to it. It is somewhat easier than scanf function. We don't need to mess with formats and so on. But then again, use whichever you find more convenient. Right? Now, turns out we can talk about binary system, hexadecimal system. We can talk also about base 64 system, meaning that we have 64 digits, not just 16, but 64, and encode information this way. Okay. So the way it's done, we borrow the letters, both uppercase, lowercase, digits, and plus and division sign. So these are the symbols that add up to 64 different digits in our new base 64 system. Okay. And why is this convenient? Perhaps because every 6 bits are replaced with 1 digit from the system. All right. And that might be convenient because it rounds up to, if we use byte by byte conversion, then every 3 bytes are going to come to 4 digits. Right? Now, if at the end it turns out that there are not enough symbols or not enough bits or bytes, then we pad them with zeros, or we fill the end with placeholder. We use the equality sign as the placeholder at the end, right? So therefore, if we take this, string, if you will, these 5 bytes, A is 65, and so on. So we have 5 bytes here, 5 bytes. And treat this as a binary value, then we can write it down using base 64 encoding. And then we need to write one equality sign at the end, right? In this case, because there are 5, there was 1 missing for the 6. So there are more encoding systems than just 16 and 8 and 2. And base 64 sometimes is used in computing, in computer science, to write down very large numbers. For example, keys for cryptography and so on. And finally, some silly things. Programmers sometimes use readable constants. We can use the digits from the hexadecimal system and make up some words. Feed beef, there should be. And dead beef, sorry. Okay, so there's a typo. Feed beef. Or did beef. So all of these are digits in hexadecimal system. But for us, if we look at the representation in, let's say, large group of data, it's easier for us to spot, perhaps, these readable constants, if you will. Okay, to mark some location in the memory. And finally, let's consider x, right? So this is like multiplication. That's what we're used to quite often. So 3 times 12 is 36. 2 times 12 is 24. 1 times 12 is 12. However, 0 times 12 is 18. How is that possible? Could you comment?
Okay, it's like hex.
And guess what? You're right. So if we are a programmer, then we right away notice this, that this is the hexadecimal notation. So 12 in hex is the same as 18 in decimal. So it's all good. And in fact, these would not compile 3x12 or 2x12 or 1x12. But for humans, we can parse them, we can read them and understand quite well. All right, so with this, I'd like to say that this lecture is over. And the next time we're going to talk about how to represent negative values in hardware. We're going to talk about 2's complement, 1's complement, and so on.